In this video, I will explain how to apply the fundamental theorem of calculus part 2. So the theorem states that if f is a function continuous on the interval from a to b, and capital F is any antiderivative of that function f, that is, it is a function such that if I take the derivative of the capital F, I get f, then the integral from a to b of f of x dx is equal to the antiderivative with b substituted in minus the antiderivative of a substituted in. So this equation is the key to evaluating definite integrals. So it says that if I can find an antiderivative, capital F of x, for f of x, then I can compute the definite integral. And I do this by plugging in the limits a and b into the antiderivative, and then I subtract. So the notation that we use is the integral from a to b of f of x dx is equal to the antiderivative represented by the capital F of x. And then I draw a square bracket, and then I put the upper and the lower limit in the corresponding spots. So let's take a look at some examples. So here I have the integral of x squared dx from 0 to 3. So the first thing I'm going to do is I'm going to find the antiderivative of x squared, which is x cubed over 3. And I'm going to draw the square bracket and put a 0 and 3, which was the upper and the lower limit. Now, since 3 is the upper limit, I'm going to substitute that in first. So I get 3 cubed over 3. And then I substitute the lower limit in, which is 0. So 0 cubed over 3. And then I evaluate. So 3 cubed divided by 3 is 9. And then the second piece is 0. So the answer to this integral is just 9. Let's take a look at the second one. So again, we find the antiderivative of sine x, which is negative cos x. And then we write the square brackets with the lower limit and the upper limit. And then we're going to substitute those limits in by putting in the upper limit first, which is pi over 2. And then we have minus and negative, so it's going to be plus cos 0. So negative cos pi over 2, if you think back to the graph of what cos looks like, that's this. And at pi over 2, cos is 0. And then cos 0, which is here, gives us a y value of 1. So we have a 0 plus 1, which equals 1. All right, let's take a look at a couple more. So this next one here, now it is probably going to be easier if we divide each of the numerator terms by x squared. And I'm also going to take the 2 that's in the denominator, and I'm going to move it in front of the integral sign. So now I have half. Remember, the 2 is in the denominator, so that's why it's going to be a half. And we have the integral from 1 to 2. So I have x squared divided by x squared, which is 1, plus, and then x divided by x squared, I get 1 over x, minus, and then we have 2 over x squared. So I'm going to rewrite this actually as negative 2, and then x with a negative 2. And then we have dx. Now I could have done that with the 1 over x as well. However, let's just keep going and I'll show you why I didn't. So the integral of 1 is x, and the integral of 1 over x is that special natural log x. And this is something that you should recognize. So whenever it's 1 over x, remember that the antiderivative of 1 over x is the natural log of x. Okay, so then we're going to integrate the last term. So we're going to add 1, which gives us negative 1. And then we would put negative 1 on the bottom, but I'm not going to do that because I know that dividing by negative 1 means that this will become positive. So the sign will change to positive. And actually, instead of writing the round brackets, I'm going to put square brackets so that I can put the upper limit and the lower limit there. So now I have a half. I'm going to put in the upper limit first. So I have 2 plus the natural log of 2 plus 2 over 2. And then minus 1 plus the natural log of 1 plus 2 over 1. Okay, and we're just going to do some simplifying. So we get a half in the front, and then we have 2 plus 1, which is going to be 3, minus 1 will be 2, and then minus 2, which will be 0. And then natural log of 1 is 0. So we actually only have the natural log of 2 left. And you can rewrite this as the natural log of 2 divided by 2 if you like. All right, now the very last one I want to show you is this one here. And it says that we're going to integrate f of x from 0 to 5. But f of x is this piecewise function defined here. So when x is less than 2, we're going to use the function 3x squared. But when the function is greater or equal to 2, we're going to use the function 2x minus 3. So we're going to split this up into two integrals. So we have 0 to 2, and then we're going to use the function 3x squared dx. So we're using the definite integral rules. So plus, and then since this is 0 to 2, this one has to be 2 to 5. And when x is greater or equal to 2, we're going to use the second function here, 2x minus 3, and then dx. So we're going to integrate each part separately. So the antiderivative of 3x squared is 3x cubed over 3. And we're going to integrate that from 0 to 2. And then 2x minus 3 is 2x squared over 2 minus 3x. And we're going to integrate that from 2 to 5. So I'm going to reduce this, so those become 1s. So of x cubed, so it's going to be 2 cubed, and then minus 0 cubed. And then these 2's will cross off to become 1 as well. So then I'm going to plug in the upper limit first, which is 5. So 5 squared minus 3 times 5. And actually, let's just put round brackets in here. And then we're going to minus, plugging in the 2. So we get 2 squared minus 3 times 2. Okay, so I just separated these with square brackets to show that this was the first integral, and then this second square brackets is the second integral. But you can actually just write normal round brackets all the way through, or not even write some of these brackets in, because they're really not needed. So 2 cubed is 8, and then we don't need the 0, so plus, and then we have here, we have 5 squared is 25 minus 15, so that's going to be 10. And then the second bracket here is 2 squared is 4, and then 4 minus 6 is negative 2, but then we have a negative sign here, so it's going to be plus 2. So then 8 plus 10 plus 2 is going to be 20. Now, one note that I want to make about this piecewise function is that the method that we used here by splitting it up is the same concept that you're going to use for absolute values. So I actually want to write this down because you're going to encounter some other ones like that too. So note, use the same concept for absolute value functions. So remember that f of x is equal to absolute x. And what you're going to do is we're going to split this up into negative x and positive x. And then you need to find out where that function, in this case, it's just x. So x would be less than 0, and then x is greater or equal to 0. If it was a different function in here, you want to find out where the 0 is, and that would give you your intervals or your inequalities here. So instead of 0, it could be a different number. So for example, let's say that if f of x is equal to x minus 3, then we could split that up into negative x plus 3, and then x minus 3. So then here we would have x is less than 3, and then here we would say that x is greater or equal to 3. And the reason that it's 3 is because that would be the value that would make our absolute value equal to 0.